Welcome back to the next video, everybody. Today we're going to cover proposition 2 from the previous video. So just a recollection of where we're at here. The main theorem is the universal deformation ring exists. So if V is absolutely irreducible as representation, then there's a ring R in C. C is like complete Noetherian local algebras, and a deformation D from V to R such that for all rings A and C, there's a bijection between C maps from R to A and DVA given by F maps to F lower star of D. F lower star was described last video. The pair R comma D is determined up to unique C isomorphism by the first property. That's just the usual category theory nonsense that guarantees you uniqueness. 3, R is Noetherian if and only if the K dimension of the first cohomology of GNKV is finite. We'll prove that later. If R is Noetherian, then R is emmatically complete, where M is the maximal ideal of R. And for each A and C, there's a well-defined bijection from O algebra maps from R to A to DVA given by F maps to F lower star of D. So last video, we reduced the proof of theorem 1 down to 2 propositions, which we called proposition 2 and 3. And in this video, we're going to prove, well, give a sketch of the proof of proposition 2. I'm not going to beat it to death with all the details. We've now sort of sketched the proof of the existence of universal deformation rings twice. So I'll be a little bit scant here, but you can see CSS chapter 9 for more on this. So here's what proposition 2 says. There is a ring RB in C and a map rho B in the rho bar maps from G to GLN of RB, such that for each A and C, there's a bijection between C maps from RB to A and rho bar maps from G to GLN of A. That sends a C morphism F to the composition of F with rho sub B, which is a map from G to GLN of RB, followed by a map from GLN of RB to GLN of A. And the pair RB comma rho B is determined up to unique isomorphism by this property. All right. So the proof goes like this. First, the final statement of the proposition. So this unique up to unique isomorphism nonsense follows from the usual uniqueness of universal objects from category theory. Okay, so we'll prove existence. First, we suppose that the group we have a representation V of is finite, and one goes through a construction process, which I won't go through the details of because it's not particularly interesting, producing special commutative O algebras OGB, where B is a positive integer, via certain generators and relations. So they're explicitly constructed, okay? As an example, OG1 just ends up being the group ring of the largest abelian quotient of G over O, okay? And then all the other ones have sort of significant meaning beyond that. One easily proves then that for every O algebra A, there's a canonical bijection from O algebra maps from OGN to A with rho bar maps from G to GLN of A. Okay, so there's nothing super interesting going on here. Now, what this tells you is that the homomorphism you have, rho bar from G to GLN of K, gives rise to an O algebra homomorphism from OGN to K. Its kernel is a maximal ideal. We'll call it M sub rho bar. We'll let RB then be the completion of OGN at M rho bar. So that's what our RB is going to be. RB is clearly Noetherian, basically because we explicitly constructed these OGNs, and it definitely lives in C because it's complete local in addition. The canonical map OGN to RB then, which we have because we took a completion here, gives, using the canonical bijection above, so this bijection right here, okay, what does that give? That's going to give you a map which we'll call rho sub B from G to GLN of RB, of course. And it will commute the following diagram by definition of rho B or rho bar homomorphism. So we have the map rho B from G to GLN of RB. Then we have rho bar from G to GLN of K. We'll put an equality here. And then we have the reduction map from GLN of RB to GLN of K. So that diagram commutes essentially by definition. Okay. Now, what you then show is that the map from proposition 2, the map right here, the map that sends F to F compose rho B, now that we have rho B, okay, the next thing you show is that that's a bijection. And to do that, you just quickly produce, it's not too hard, for any A in your category C and any rho in rho bar maps from G to GLN of A, a continuous O algebra homomorphism, which we'll call F hat from RB to A, commuting the following diagram. It's a similar diagram as the one we just had above that commutes, but the K down here has been replaced by an A, okay, where A is kind of an arbitrary element of C, okay? It's not too hard to do that. But then it's kind of immediate that F hat is uniquely determined by the conditions, A, that it be continuous, and B, that this diagram here commutes, which finishes the proof in the case that G is finite. Okay, so what if G isn't finite? Here's what you do. You set G equal to the inverse limit over H, where H ranges over the discrete quotients of G, for which rho bar from G to G ln of K factors through a map, which we'll call rho bar H from H to G ln of K. Each H is finite by discreteness, so the construction above that we just went through produces a ring which we'll call R sub H and C, together with a group homomorphism H to G ln of R sub H, reducing to rho bar H from H to G ln of K. Okay, that gives me a projective system RH over the H and C. And then naturally, what do you think I'm going to do to produce my overall RB? I'm going to take the inverse limit over all the RHs. Okay, we do have a continuous map rho B from G to G ln of RB induced by the composition maps G to H to G ln of RH. It's easy to check that RB surjects to each discrete Artinian quotient of RH using the above. And it's also easy to check that every discrete Artinian quotient of RB arises in this manner. In particular, RB has to be in C, okay, which is where we need it to be, or else it's not a universal deformation ring, okay? So finally now, what you do is you take A and C and you write it as an inverse limit, projective limit of its discrete Artinian quotients. And then I'm gonna tell you how to finish, and maybe you can do it as an exercise now. Basically, the finite case that we did first, and then the case where G is written as the inverse limit over its discrete quotients through which rho bar factors come together once you write A as this limit. And they give you the general case. And here are the facts you need to finish, I'll tell you. Hom rho bar commutes with the inverse limit over I. Hom rho bar H commutes with the limit over H. And all these are basic kind of category theory / homological algebra facts, okay? We also have the canonical bijection in the finite case. You'll need that. We also have that the limit over H commutes with O algebra homomorphisms. And we also have that the inverse limit over I commutes with O algebra homomorphisms. If you put all that together along with the finite case, we find that Hom rho bar from G to G ln of A is isomorphic to O algebra maps from RB to A, which is exactly what proposition 2 claimed. And of course, we're considering continuous homomorphisms on each side. All right, so there, if you go back and watch the previous video, there is another proposition 3 that we need to finish the proof of part 1 of theorem 1. Part 2 of theorem 1 was usual category theory nonsense. Part 3 of theorem 1, we still need to take care of. That will follow from proposition 1, which we have also not proven yet. Okay, and then I think 4 will follow as well. Well, I think maybe 4 follows from proposition 1, and then R is kind of number 3 is kind of a separate argument. Okay, so we'll begin tackling proposition 3 to finish part 1 of theorem 1 next time. So I'll see you then, and thanks for watching.